Cool. So today we're talking about the ABCI. And so this is the application blockchain interface. This is the interface between Tendermint core, the replication engine, and the state machine, otherwise known as the application, that can be written in any programming language and has kind of become one of the defining features of Tendermint core as a product, enabling blockchain apps to be written in any language. So today we'll cover kind of the motivation for the ABCI and how it works in a little bit lower detail, with an ultimate goal, I would say, of being able to work towards a more formal specification for the semantics of the ABCI and of how Tendermint interacts with applications. So I'm going to share my screen here. Just a second. So what I have here is a presentation I gave earlier this summer. And some of this was heavily inspired by presentations that Sunny has given. So I'll give him credit. But I think his slides have been designed by Peng and so are much nicer than mine. But anyway, the basic idea here is that, typically when we're talking about products that implement consensus for the real world, they're typically implementing state machine replication, which means that there is some state machine, i.e. the application, that is being replicated on many computers. And we want them to be replicated consistently and for them to stay in sync and so on. And the way this has traditionally been done with products like Apache Zookeeper and etcds, CoreOS's etcd and HashiCorp's console and so on, is a kind of monolithic approach where you have basically a single binary that contains all of the pieces, and they're reasonably, they're relatively integrated with each other vertically, right? So we can kind of think about the three layers as the networking layer where you're communicating with your peers, the consensus layer where you're actually implementing the protocol for we might call atomic broadcast or state machine replication, or consensus in the most basic instance, and then there's the actual application. And typically in like for Apache Zookeeper and CD and so on, the application is really just a fancy key value store. It's usually like, it's got features of a key value store, but maybe oriented towards service discovery and things like this, right? Of course, there's also Bitcoin emerged, and Bitcoin fits nicely into this model as well, where the application is not just a key value store. It's actually a functional programming language over a cryptocurrency, right? So there's the Bitcoin scripting language. It's purely functional. So there's actually no persistent state other than kind of the state of these functions, and the outputs of functions are consumed, and the inputs are the outputs from previous transactions are consumed in inputs, and so on. You get this chain. So those are all just application details. It doesn't matter. But the point is you can have interesting applications as the state machine that's being replicated, but traditionally it's all been kind of vertically integrated into a single stack. So then you had Ethereum come along and other variants where, the different projects Ethereum has inspired, where instead of a hard-coded particular application, you have a hard-coded virtual machine, a full-blown virtual machine with internal state and everything. And that allows you to build your applications on top of that virtual machine and to upload them at runtime and so on, which is quite nice. But you still have the same problem of the application being to the product, right? You're stuck with whatever virtual machine was defined, and you don't really have flexibility over that, right? And so you're still dealing with what I call somebody else's state machine. And so the grand idea behind ABCI is to split that, is to actually separate the application layer, the state machine, from the replication layer, which is the consensus and networking, and have it communicate over a well-defined interface that is sufficiently well-defined that it could actually happen over a socket, i.e. with another process, right? So the application state machine can run in one process, the replication engine can run in another, and they can communicate with each other over this ABCI. And so basically what the ABCI has to facilitate is transfer of the information that we're coming to consensus on to the application so that the application can interpret it and return certain results. And there's a lot of subtlety around exactly how that happens, and the different ways that information needs to be communicated over this interface, and that's all the gory details we're going to go into here. So before we go and do that, are there any questions so far? I will take silence to mean no. So jumping down to it, one analogy that we like to make is that the ABCI is a interface between a replication engine and a state machine, in much the same way that something like CGI is the interface between an HTTP web server and an HTTP web app. So in the same way, you have this kind of separation in the web application domain between the web application, which actually implements, the state machine, and the server, which handles all the security and networking and so on. You have the same separation in the Tendermint world, where you have some state machine, some application, like for instance the Ethereum virtual machine. So this is the product that's called Ethermint, where we have the Ethereum virtual machine running on top of Tendermint, and then you have your security and networking layer, which is Tendermint. And the only real difference between these two worlds of the web and blockchains is that in the web case, the Apache web server here is only running on a single machine. So it's just not replicated. Whereas in this case, you have this whole stack running on many machines, and you're fault tolerant across them. So the only real difference here is on the right side, we have added fault tolerance, whereas on the left side, we don't necessarily, right? But otherwise, the kind of analogy is very strong. And so in the same way that when you're communicating with this web application, it's all happening by HTTP, and it's all mediated from via some front end server. When you're communicating with this application, it's all mediated via some Tendermint server, right? So all client communication actually passes through Tendermint, and Tendermint deals with forwarding information and getting responses from the application in the same way that the Apache web server or the Nginx web server forwards HTTP requests to a web application and handles responses that it then sends back to the client. You can see my mouse, right, as I'm pointing to things and saying this or that?
Yep.
Cool. Okay, so a little bit more fine-grained detail here then. So, here we have a big gray box, which represents basically one full node, one computer. Here we have a client, and we think about having two processes running on this computer. One is the Tendermint core process, right? So this is Tendermint in Go, as we're all familiar with. And then we have an application process. And this could be an application like Gaia, like the Cosmos Hub. It could be an application like Ethermint, where it supports the Ethereum virtual machine. But it could also be anything else. And while a lot of the applications we write are written in Go and actually compiled with the Tendermint as a single binary, it's helpful for the discussion of ABCI to treat it as if it's an independent process, and that you're dealing with, asynchronous socket communication between the two processes, or at least concurrent sockets between the two processes. And that when you compile it into the single binary, it's just a special case where the socket communication collapses to function calls. Does that make sense?
So if you don't compile it in a single binary, what does it communicate over?
It communicates over a socket like IPC.
Okay.
Right? So you could set up a TCP socket, or you could set up a Unix socket, and then it just uses the operating system's native IPC mechanism, like inter-process communication mechanism, to deal with that. So, but it's specifically using a socket rather than some kind of like shared memory or a file, even though sockets are technically just files from an interface level. But so, on a single machine, you could use TCP. Of course, that would have a little bit extra overhead because you have the TCP protocol, or you could just use a Unix socket, in which case it'll be a little bit more performant. Because you don't have to deal with the networking stack. But in both cases, it's semantically the same. You have, reliable ordered delivery across a socket between one process and another. So
was there a specific reason why, say, Gaia was decided that it would be built in the same binary, or just ended up?
Because it's written in Go. So when you have when you have an application that's written in Go, it's quite convenient to just compile it into a single binary. it will give you more performance because you just have function calls instead of inter-process communication. And B, it's operationally simpler because you only have one process to run instead of two.
Got it.
So I believe it is possible to run Gaia in a separate process. I think there is a like without Tendermint flag or something like that, so that you can start Gaia in one process and start Tendermint in another. But the default behavior is for them to just operate as a single binary, because that's more performant and more convenient operationally. But if for some reason you want to, you may want to run these on different machines. You may want to say, I want dedicated hardware resources for the replication engine, and I want dedicated hardware resources for the application, and I'll run them on two physically distinct machines, and they'll communicate, actually over an Ethernet cable. And that's totally fine. The architecture supports that. Make sense?
Yep.
So one thing that's in this diagram that we haven't discussed yet is the fact that there's actually three connections between the Tendermint process and the application. And those are indicated here by these blue diamonds, right? And the reason there's three connections is because there are three kind of fundamental concerns of the ABCI that need to be captured. And those concerns, we want them to be concurrent with one another so that operations on one don't block operations on the other. And so those concerns also map quite directly to the statefulness of the application and the expectations that the ABCI protocol kind of places on the application for managing state. And so those concerns are basically, we call them consensus, mempool, and query. So consensus is kind of the most obvious one. This is where we've come to consensus on a block in Tendermint. And now that block has been committed, before we've even, blocks in Tendermint are committed before any of the transactions are actually processed. So Tendermint has no idea what is the content of a block from in terms of the transactions before it gets committed by the validators. And once it's committed, then we use the consensus connection to actually transmit all of the contents of the block to the application so that the application can execute the block and return the results. And that's how, that's where all the signature verification happens. That's where like the main state transitions happen in the state machine of the application. And that's where results can ultimately be returned. And the effect of those results can be indexed by Tendermint so that a client can later query and say, hey, Tendermint, give me the result of this transaction. And even though Tendermint doesn't have the competency within itself to execute the transaction, it stores the transaction and the result it got back from the application, right? And so all of that is due to this consensus connection where we're forwarding all the contents of the block to the application and getting responses. This is also where the application is given the opportunity to update the consensus, right? So the consensus defines a set of consensus participants, which we call the validators. And with each block, the application has the actual opportunity to update the current active set of validators. So we'll see in the ABCI messages coming up that the application can actually return results that tell Tendermint how to change the validator set. And because the application is executed deterministically and strictly as a function of the block, which was committed correctly by more than 2/3 of the validator, those responses will be deterministic. And so these validator changes will be just a part of the consensus process and will be agreed on by all the validators, right? And so we don't have to treat validator set updates as some like different mechanism within the consensus. It's just kind of dealt with by the ABCI, and we can actually delegate control to the application. So hopefully that'll become more clear. Sorry, go ahead.
Inside the consensus and the blockchain, in data structures, I've seen that basically just the hashes for the validators are stored, right? Is this true? So if the client wants to get the actual validators, it has to go through the application. So the application actually stores the validators, or how does it?
Very good question. In most cases, for most sophisticated applications, the validators will be stored by both Tendermint and the application. So Tendermint definitely stores the validators always, and it keeps them on disk and manages them itself. But there is some expectation in, Tendermint is designed with some expectation that the validators won't change that frequently. It's not, it doesn't depend on that, but it basically uses that to optimize the storage of validators. So Tendermint stores validators at every height that they change. And so you can always query the validator set from Tendermint, and you can check that the validator set matches the hash in the block. But we don't actually include the validators directly in the block itself. It's more expected to be, derived deterministically from the initial validator set, which everyone has to agree on in the Genesis block, and then from, the transactions, which everyone executes deterministically. But for the application to competently manage the validator set, it needs a representation of the validators itself. And because there's no actual shared memory or shared databases between Tendermint and the application, that effectively means that the application has to duplicate storage of the validator set in the application state. And so in sophisticated applications, you'll have the validators stored redundantly, both in Tendermint and in the application.
Yeah.
That makes sense?
I also have a question.
Yeah.
So the application, where is it deployed? Is it deployed together with validators on the same machine, or?
Yeah.
What?
So every full node, when we say a full node in a Tendermint-based network, we're looking at a box like this. So every single full node is running both the full Tendermint replication and the full application. And typically these are compiled in as a single binary. In some cases, when it's written in another language or for operational reasons, they'll run as separate binaries, like separate processes. But in any case, the definition of a full node includes both of them.
What are use cases when application is outside the full node box? Like if they're in like separate machines, is there a use case for that? Or?
So, okay, two things. First, by definition, a full node is someone that runs the application. Whether the full node spans multiple pieces of hardware is kind of an implementation detail. So there may be, like I was saying, you may want to have dedicated hardware resources for Tendermint and dedicated hardware resources for the application, in which case you can imagine having two servers, one to run the app, one to run Tendermint, and have them communicate over Ethernet. And that's fine if you want to take that, very, if you have very high requirements, very high hardware requirements, if you're expecting to manage, a huge number of peers, and maybe you have very high computational requirements on the hardware and you want to take as much advantage of concurrency, for instance. So your application executes transactions concurrently and Tendermint's managing peers concurrently. So maybe you want to have dedicated hardware for both. But regardless of the hardware setup, the full node definition includes both. That said, there does seem to be some demand and some use case for nodes on the network which are not quite full nodes, i.e. which do not run the application logic. And this is really just for helping with the peer-to-peer layer, right? So you could imagine nodes on the network that are only offering peer exchange. So their only purpose is to help peers find other peers. And for that, we don't really need those nodes to run the application. And so you can imagine a version of Tendermint that is able to operate without the application that only runs, say, the peer exchange. And maybe there are modifications we can make to allow it to only run, say, the blockchain reactor so that it can help other nodes sync the blockchain, but it can't actually grow its own blockchain because that would require an application. Or if it didn't have the application, it wouldn't be able to do the full verification, right? So it could still do consensus and trust the output from other validators, but it wouldn't be able to verify that output itself because it's not actually executing the transactions through the application. So there does seem to be some demand for nodes that do that and to play a supporting role on the network and to potentially lower the attack surface of executing transactions, which is where a lot of the complexity lies. But to date, that's not really well supported in the Tendermint product. It's something we've discussed about supporting in the future.
The link that I put in the chat is the Polychain Labs actually created a seed node that does exactly that. So it's called Tender Seed.
Right. So I believe they only run the PEX, the peer exchange reactor, and none of the others. Cool.
So, and one more question. What about the client? Is it also trying to follow application logic, or it can do whatever it likes? So what are the expectations?
The client can do whatever it likes. And depending on, it really depends on what the application is, right? So that will determine how the client interacts. So you could imagine a version of Tendermint that is purely atomic broadcast, which is to say there's no state machine, that all it's doing is totally ordering a series of transactions where there's no other requirements on the validity of those transactions. It's just transactions are sent to the network, they're put in an order, and there's agreement on the order. And in that case, the only thing the client is trying to learn is the order of transactions, and all kind of application logic and processing and so on would happen client side. And then, so that's on one extreme. On another extreme, you have an incredible amount of application logic happening, for instance, on the Cosmos Hub, where you have all this proof of stake economics, all this validator set activity, there's governance, there's, account balances, there's soon going to be IBC, all this stuff. And in that case, a client is going to be very interested in what's happening at the application side, and just looking at transactions, won't be sufficient. Even just looking at transactions and results won't be sufficient, because there's a lot of state that's actually stored and managed by the application that the client is interested in. And so a lot of the client's queries are going to be actually, tell me the current state of the application, tell me, really it's not going to get the whole state, because the state could be massive. It'll make some query about the state, like, give me this current account balance, which is only stored in the application. It's nowhere to be found in the Tendermint blockchain, right? Or it could say, give me the current number of votes on this governance proposal, or whatever it might be. That answer the question?
Yeah, thanks. But in principle, client can be as faulty as it likes, right? There are no guarantees.
Yeah. Absolutely. There's no dependence on the client here.
Cool. I got it. Thanks.
Yeah. Okay. So we talked about the consensus connection, which is really the main thing. But then for queries, when the client wants to actually query something about the application, we don't really want those queries to compete with the consensus activity. And furthermore, while the consensus activity is taking place, for instance, between the time when we've committed a block and finished processing the block, right, we want clients to still be able to make queries, because actually executing the block could take some time. And so we want those queries to run concurrently. But what's important is that those queries happen against some consistent state. So the state that the queries are made against is the last completely executed and committed state, which might be different from the latest state in the midst of the consensus processing, right? So while we're processing a block, we actually process the block one transaction at a time, and that's leading to state updates on the application. And so the application is basically expected to maintain distinct states for each connection to support reads and writes on those particular connections. Now, in fact, on the consensus connection, it's really just writes. We don't do reads on it. The reads all go on the query connection, and the reads are expected to be from the last committed state, so that when you read over the query connection, you're not actually reading from the state in the middle of a block, because the expectation is that blocks are committed atomically. And so the state in the midst of the block actually shouldn't be exposed to anyone until the block completes executing.
So in this case, when you say expect, it's really just up to the application developer to sort of ensure this.
Yeah.
Tendermint does not have anything like any mean to ensure that you are not keeping the one state and just concurrently returning and executing the transactions against it.
That's right. Technically speaking, this is up to the application. And what I'm hoping to achieve actually is a lot more clarity at a specification level on what are actual requirements and what are standards. And I think there's been, there's a lot of flexibility here, because the core definition of the ABCI is a protobuf file, which just is really just the syntax. It just defines the message types. But there's a lot of detail and a lot of subtlety and a lot of requirements in the actual semantics. And some of those semantics Tendermint really depends on, and some of them are more convention for building clients and building applications and having kind of a consistent understanding of things. And so some of those conventions may be violated for certain applications. Maybe you have an application with very strict performance requirements where this strict separation or, you know, strictly atomic commitments of blocks isn't as necessary. And maybe it's okay for those applications to expose, you know, intermediate state, say. But in general, we've tried to put together conventions for how applications should be built and how we tend to build applications that are kind of more, say, sensible and maybe more best practice and easier to reason about. But those conventions mostly aren't actually enforced or aren't really capable of being enforced and are more just expectations.
Cool, but like in the future, do we want to try to somehow codify these best practices?
Yeah.
I mean, still having flexibility, but I don't know really what is the best way to do this. But like, ideally, we kind of want to formalize on this so that when you are developing application, you sort of have some help, like maybe by introducing some abstractions, so you know.
Yeah, absolutely.
Like, okay.
Yeah, and so, you know, this is actually the reason, one of the primary reasons that we build ABCI frameworks like the Cosmos SDK, right? So the expectation, so everything we're talking about is very low level, right? And we actually don't expect application developers to write applications against such a low level API, because there's a lot going on here. They have to worry about, you know, these concurrent connections. They have to worry about, you know, statefulness and, you know, copies of state and something that's like a, you know, like concurrent control over those distinct states and so on. And so really we want those kinds of concerns to be handled by the application framework developer, so the people building the Cosmos SDK. But the actual application developers, which for instance would use the Cosmos SDK, shouldn't have to think about these things, right? And it's kind of the same in the world of web app development, right? You don't expect every web developer to be programming against the low-level details of HTTP and, you know, implementing specifics about parsing HTTP requests and the semantics of HTTP timeouts and, you know, headers and all this kind of stuff. All of that tends to be dealt with for you by an HTTP framework, and then you program above the framework. You build your application within the framework. And so really all this low-level detail is really only important for the developers of frameworks and for anyone who's crazy enough to think that they have needs that are not covered by a particular framework. But if you would go and look at the Cosmos SDK, for instance, all of these conventions that we're kind of talking about are implemented already by the SDK and taken care of for you by the SDK, so that you don't have to worry about them when you program your application. Make sense?
Yeah, so as far as I understand, you have an API, right? And it's just syntactic, right? So you have constraints on what you can do and what you cannot. But what you'd rather have, what you like to have is something more like a state machine or contracts, right? If I do this, eventually I will get that.
Exactly.
Or if I did that, I cannot do something else.
Exactly.
I see. But that's also for like really like hardcore developers, right? Not for normal users.
Yes.
Okay.
But insofar as we are trying to grow the ABCI ecosystem to many languages, it means we need robust implementations of ABCI frameworks in each of those languages. And in order to get, you know, expert developers to really be able to build those kinds of frameworks, we need to have very clear specifications on what the expectations are, so that they can, you know, they can build against those, and we can write tests to see that they satisfy them and so on. And so really, yeah, we want these specifications for to provide clarity to the people basically building the application frameworks. And it's those people's responsibility to then expose, you know, specifications or documents or APIs to the actual application developers who decide to build on their particular framework.
So right now, just a tangential question. The SDK is really the only framework that exists, right? That you know of? No?
No, there's Lotion in JavaScript, which deals with a lot of this, but maybe takes a simpler or more naive approach to some things, but it's still actually quite advanced after the SDK. And there is a Haskell framework in the works that is joint collaboration between the Foam team and the Kadena team, and they're funded by the foundation. So that will be probably the third most advanced framework, because they're basically working to build something roughly compatible with the SDK.
Cool.
Maybe we can also assume that Tendermint is also a framework for building application, because it also hides the ABCI.
No, Ethermint is built using the SDK.
Okay.
Yeah. So the SDK is actually the framework used to build Ethermint. So the people who are implementing Ethermint, like the ChainSafe developers, they're programming against the SDK. They're not programming against the ABCI, right? And that's really important, because it means the SDK developers have done a great job actually building a framework to make it easy for application developers to build on top of even very complex advanced applications like Ethermint, without having to really dive into the lower level details of the ABCI. Of course, they're going to have to understand some things about it, but they don't have to program directly against it. The SDK takes care of quite a lot of things for them. Really, I would say if you're really interested in what the key thing is that the SDK is doing here, it's the base app. So there's a package in the SDK, which is really the lowest layer of the SDK, which is called the base app. It's not actually that much code, and it's basically a first layer of abstraction above the ABCI that really defines how we manage state and how we provide application developers hooks into the various ABCI messages. And so if you're interested in how that works and you want to look at the SDK, but you're overwhelmed because the SDK has a lot of code, the only thing you really need to look at is the base app. And so when we talk about the Foam team building something roughly compatible with the SDK, really we're talking about those kind of base app constructions. And then above that, some of the more particular types implemented in the SDK, like the coins type and the accounts type and so on, which are just like, standards for building cryptocurrencies, but aren't really part of abstracting over the ABCI. They're more particular to the kind of state machine you want to build. Whereas the base app is really the first layer abstraction over the ABCI to enable people to build more advanced applications without worrying about all the low level stuff. Make sense?
Yeah, so I'm just curious, did you find any discrepancies already when you had this Cosmos SDK and this in Haskell, for instance?
The Haskell development is only a couple months old. So they've just started the development, and we haven't really started any kind of compatibility testing yet. But that will probably be happening over the coming months. So we'll be looking for inconsistencies. And the goal is really to be able to run a network with a simple application, written in the Cosmos SDK and one written in the new Haskell SDK, and see if we can break it. And if not, that'll be a good sign. But really, we need more. The goal of those contract tests and specifications is to be able to write a more formal test suite to ensure compatibility between different implementations.
Right, because it's hard to imagine what they can do to each other, right? They can kind of slowly poison each other somehow in incorrect data. The two different implementations.
Possibly. The thing is, though, which is very powerful, is we use cryptographic hashes of the state at every block to ensure consistency. And so you detect very rapidly if there is any kind of divergence, to the extent that you're hashing all of your state, right? So of course, certain applications, they don't hash everything, and the results aren't currently being hashed and so on. But the state itself is typically hashed in some kind of Merkle tree, and that gives you, that tells you very quickly whether or not, these implementations are doing something different. But that's just with respect to the state changes. That doesn't necessarily assure that you have the same kind of behavior in terms of these concurrent ABCI connections with the mempool and the queries and so on. And that'll be much harder to test for.
So you talk about the two. How about mempool? What's that for?
Yep. So the consensus is for actually executing the block. Query are for sending client queries to get some information out of the state. The mempool is for the mempool, right? And so the way Tendermint works basically is a client sends a transaction, and Tendermint doesn't know anything about the semantics of the transaction. As far as Tendermint is concerned, the transaction is just arbitrary bytes, right? And so in order to prevent malicious clients from overwhelming the Tendermint node with bogus transactions, the transaction is forwarded over the mempool connection to be checked by the application. And these are rudimentary checks. They don't do the full state machine transition. They just do, basic checks on the validity of the transaction to determine whether or not it's worth it for Tendermint to expend resources trying to get that transaction committed into consensus, right? And so the kind of checks you might do are a signature validation, a check for account permissions, a check for, economic checks, like whether the account has enough money to pay the fees, whether the fees are sufficient to cover kind of the resources requested by the transaction, and so on. It's really up to the application how it defines these kinds of checks. But there is some expectation that the application implements some kind of validity mechanism that prevents denial of service attacks against the Tendermint mempool, right? And to be clear, the mempool is basically the pool of in-memory transactions that Tendermint has received from clients that have not yet been committed in consensus, but are eligible to be committed in consensus. And so once a transaction successfully passes through the mempool ABCI connection, it's stored in the mempool in the Tendermint node and is eligible for consensus and gets broadcast to all other Tendermint peers until it ends up in a block. Does that make sense?
Yeah, so when we talk about, again, this framework logic, so how these mempool concepts translate somehow to the, for example, Cosmos SDK layer?
Yeah, so at the Cosmos SDK layer, there are flags that allow an application developer to switch on the logic it executes, right? So that when it's in the checktx mode, the application developer can selectively execute less logic than when it's in the normal deliver TX mode. Sorry, we haven't really gone through the messages yet, and now I'm just kind of using the terminology, but effectively the workhorse of the consensus connection is called deliver TX, where each transaction that was committed in a block is actually delivered to the application. And the workhorse of the mempool connection is called checktx, which is roughly equivalent to deliver TX in terms of the message structure, but has a semantically distinct meaning because the transaction hasn't actually been delivered in consensus. It's just being checked, right? And so at the framework level, the framework will typically expose to the application developer whether a transaction is being checked or delivered. And if it's being checked, the application developer can choose, for performance reasons, to execute less of the full state transition and only do some basic validity checks. Now, it may wish to have some, not just validity, but actually some stateful transitions in there so that, for instance, you can have multiple transactions in the mempool which are dependent on one another before any of them is actually delivered in consensus. So for instance, Jarko, if you have an empty balance in your account, and say we have an application that has some notion of accounts and coins, and I want to send you a transaction that sends you, 5 Atom, and then you want to send immediately a transaction that sends those 5 atoms to Joseph. If the mempool were not stateful, right? If the application logic for the mempool connection did no stateful transitions, then we would have to wait for the first transaction to commit before the second transaction would be valid in the mempool. But if the application logic does allow some stateful transitions, then we can send both of those transactions rapidly, one after another, and they can both be waiting in the mempool and valid in the mempool before they get committed in the consensus.
Okay, so there's again some kind of pretty strong assumptions we are making on the ordering of check TX or these mempool calls, which ensure validity of transactions.
Yeah. And so there is a link between the kinds of guarantees you want to provide clients and the work you have to do as an application developer, right? And, you know, thinking about performance from an application developer perspective and how you can reduce the amount of work done from a, you know, execution point of view, but still be able to provide the strong guarantees to clients. And so the idea with the kind of check TX is to find that balance so that you don't have to do a full state transition, but you can still provide strong guarantees to clients about, you know, the validity of transactions in the mempool before they've been committed.
Cool. Thanks.
Yeah. So there's actually quite a bit of sorry.
So these checks, these basic checks, these are done locally on one machine. It's not going over the network yet.
Correct.
Okay.
And keep in mind, the mempool state is not replicated. There is a best effort broadcast service, like a reliable broadcast protocol effectively, but it's not guaranteed to be consistent. And so the mempool state on each machine can be different and yet valid with respect to that machine. You could think of it, you know, from the BFT literature as something like optimistic execution, but it's not really conceived as part of the consensus protocol. So there's no kind of complicated recovery. It's just more like the reliable broadcast that gets transactions, that disseminates transactions and structures them correctly on each machine so that they can be, so that they're eligible for consensus and that they're already ordered correctly from the perspective of the state machine once they might enter consensus. And so really the guarantee that we're trying to provide at the mempool level is that if a sequence of transactions are valid in the mempool of a particular node, then that node could be the proposer in the consensus and could propose that sequence of transactions in the same order. And if that proposer is correct, then that sequence of transactions would be correct for all the nodes once they execute it in consensus, even if it conflicts with the mempool state, right? And so this is where the importance of the kind of distinction between the mempool state and the consensus state comes into play, because what you're being asked to commit in the consensus state might conflict with what you've got in your mempool state. And so you have to be willing to throw away the mempool state and replace it with the consensus state and then kind of replay all your mempool transactions. And so there's quite a bit of subtlety in here that's been difficult to really capture in specification, and, you know, has constantly leads to questions from developers about how this should work. It's gotten better because it's just kind of been implemented for you at the SDK, but of course anyone else implementing directly on top of the ABI needs to wrestle with these kinds of issues.
So in terms of liveness, you require that the node becomes the proposer in order to get the transactions through, because the mempool doesn't guarantee that it's delivered everywhere, right? Well,
I think the mempool, so I'm not 100% sure. The mempool does not guarantee total order, but it should guarantee reliable broadcast.
Okay, I see.
So
okay.
If I'm not mistaken, the mempool is like a reliable broadcast mechanism, whereas the consensus is actually an atomic broadcast mechanism, right?
Okay, makes sense. Okay.
The consensus takes the kind of results of the mempool's reliable broadcast and turns it into an atomic broadcast where now you've actually got these things in order. But once a transaction passes the check TX, the Tendermint mempool will then try to ensure that it gets broadcast to all the other peers. But
one way to think about this is that we are essentially building local orders at each mempool instance, and then one of these local orders of transactions is being eventually committed, and then it's effectively total order. Exactly. And then the others are essentially reset, and we do this for each height or for each consensus instance. Exactly. We sort of kind of reshuffle at the end of the commit the ordering, because we throw away committed transactions And then we continue by building these local orders at every mempool instance.
Exactly.
And okay.
So it is exactly like speculative execution in CPUs, right? Where you have a series of guesses, and then if you guess right, then you get to be faster. Otherwise, you have to throw it all out and start again.
Yeah. So it is like speculative execution in the sense that you execute part of the transaction before you actually know for sure that you should execute it. But it's unlike it in that you don't actually get to benefit really from the result. It's not a performance, speculative execution in CPUs is a performance improvement. This is not a performance optimization. This is really more about providing some initial guarantees to clients and protecting the mempool, really protecting the resources.
Okay. So there's the application itself couldn't use this mempool to derive any performance gains.
It could, but that's complex, and I don't think anyone currently does that. But you're right, it could. It absolutely could. Yeah, because you can imagine once you've checked a signature in the mempool, you don't have to ever check that signature again. And so when you see that transaction actually be committed, if you know at the application level that you've already verified the signature in the mempool, you don't need to waste time verifying it again in consensus.
What's the danger of doing that, though?
Well, the danger is that you implement something wrong and then you accidentally don't verify a signature that you should have verified. It's very tricky and subtle to implement these kinds of, memoizing validation, right, is very, very tricky. And we've seen in production implementations of blockchains, we've seen the experts get this wrong. I think there was even something in Bitcoin not that long ago where, they tried to memoize a validation result, and then they ended up with a path that actually expected the validation to have happened where it didn't. And so they ended up accepting things. No, sorry, it was in parity. I think it was in parity. Anyways, it doesn't matter. But I recall this happening sometime last year, this exact issue. And so in Tendermint, we checked the signatures like 4 times. Like it's obscene, but we haven't put in the work to actually ensure that we can basically cache those results and not do it again, which would give us significant performance improvements, but hasn't really felt worth it yet.
It feels like that's some kind of staging where, again, these stages are formally specified and we have a clear requirements might be a way to go. And so that like the mempool or this check TX is just, let's say, go over first 2 stages. And then once the block is committed and you're in the right order, you just continue with, let's say, maybe 2 more stages of execution.
Sure.
So that it really kind of natural flow with a clear and not just best effort right now that you don't mess up things.
Right.
So there is probably quite some space for improvements here, how we can kind of make this more modular and more performant.
Definitely. For now, the expectation is that you'll just do all the validation during the consensus, but there's definitely a lot of opportunity to benefit from the work you've already done at the mempool level.
I have a question though around the mempool operation in that, is there any reason why, or what are the reasons why we couldn't just broadcast the transactions to the next proposer as opposed to flooding the network with transactions?
Great question. This is the kind of optimization that is ubiquitous in the literature. The reason we can't do that is because we don't actually know which node is the proposer.
Yes.
Because we don't have a link between node ID and validator ID. And this is critical for protecting validators essentially, and proposers, especially in the public adversarial setting. Now, in a more trusted enterprise setting, you absolutely could make this kind of optimization. But because, a chief goal for Tendermint has always been to operate in the public adversarial setting, we don't make it yet.
And there is no way to still maintain those kinds of privacy guarantees while still routing those transactions to effectively what is going to be the next proposer. Like there is no sort of algorithm along those lines that can provide both, that meet both sets of requirements.
Be some very fancy crypto stuff that you could do, but I don't have a clear sense of exactly how that would work, right? Because the problem is, you know, you're talking about routing, which means you're talking about like IP addresses, right? But the key thing you want to avoid is coupling an IP address to a validator ID.
Yeah.
And being able to know for certain that this IP corresponds to this validator. Because as soon as you can do that, you can try to attack that. You can try to attack that IP address by flooding it and making it very difficult for them to propose. And this is especially problematic because we have a deterministic round robin proposer. If we had a more randomness based proposer mechanism, maybe there's something you could do, but still it seems like if you can target a proposal, if you can target transactions to the proposer, then you can target denial of service to the proposer. And so I'm not sure there's really going to be a way to avoid that.
I'm just thinking in terms of scalability of the network over the long run. I mean, if you get to thousands of nodes and you have to flood the entire network with thousands of validators, and you have to flood the entire network with transactions, you're going to start encountering like large scale bottlenecks in the flow of transactions. So there must be some kind of, or I suppose it's then an open research question. How do we then optimize the bandwidth flow?
One of the sort of key difficulties here is the fact that we are in a gossip network. So we are just connected to a subset of peers. And so any sort of point-to-point communication pattern or like many to one are very hard to implement because we sort of, what we have available is just a broadcast essentially. And so anything else would be pretty complex, and it would involve some kind of routing, which right now seems very complex. Yeah. So in terms of scalability, what we are thinking about, like more short term, is just having more clever mempool gossip protocols, which will be using resources in a more smart way than just flooding the network like we do right now. Mm-hmm. But probably not like introducing more complexity at the like protocol or this kind of router logic.
Yeah. Okay.
Kind of a side question, like how would like a option in the ABCI in the sense of like something like deliver block change this?
We'll get to that.
Okay.
Yeah. Any other questions about the kind of this concurrent setup, why we have 3 connections, the relationship between mempool and consensus and query? The other thing that I haven't said explicitly, but has kind of been hinted at, is that so essentially the idea here is that the application maintains a distinct state for each of these connections. And those states are synchronized after a block completes execution. So the idea is that there's a state for executing the block, there's a state for executing mempool transactions, and there's a state for running queries. The state for running queries only changes once a block is fully executed and committed. And so the state that you run queries against is always the latest fully executed and committed state. The mempool state changes with every transaction in the mempool, right? And keeps some rudimentary stateful information about those transactions. But that state will never, ever, ever be committed. And we actually don't even really expose a way to query against it, I don't think. Because it's really just for checking validity, right? And that state is reset. All the states are reset after a block is fully committed and executed, so that they're basically synchronized at the start of every new block, right? And then the consensus state is only updated once a block is committed in consensus. The transactions and the different pieces are executed one at a time until it's finished and the block is actually finishes execution. That gives us the new resulting state. And then the other 2 states are set to be equal to that one. And then at that point, all 3 states are identical once again, and then they can start to diverge for the next block.
So yeah, this is very interesting. So it seems that like if we would have really named these 3 states differently, we could actually formalize relations between them. and really like the protocol for updating them.
Yeah.
And yeah, this seems really like a way to go, because it might simplify really logic a lot. And also, I think that then like mempool is just seen as updating one particular kinds of the state, and then you can really reason about it in isolation, and then just relation between this state and let's say the query or consensus state.
Yeah. Yeah. So
sorry, one thing I still don't get about the mempool is, so you keep collecting transactions, and once you have committed a block, what do you erase from the mempool? Does it stay the same size, or is it like
excellent question? No. So what we do is we delete all transactions from the mempool that were committed in the block, right? And we reset on the application side. So Tendermint does that. It deletes all transactions that were committed in the block. On the application side, the mempool state was expected to be reset to the result of committing the block. And so now you're left in this situation where you have a whole bunch of other transactions potentially left over in your mempool. And given that the state has actually been updated, you actually now don't know if those transactions are still even valid. And so what we do is, after we finish executing the block, and after the mempool state has been updated on the application side, and after all transactions that have been committed in the block have been removed from the mempool, we then take all remaining transactions in the mempool and rerun them against the mempool state to see if they're still valid.
So what does it mean to rerun them?
It means to resend them over the mempool ABCI connection, to call check TX, and to say, look, application, we understand you've just updated your state. We have a bunch of transient transactions here that have not been committed. Tell us if those transactions are still valid with respect to the new state. And if they're not valid, we'll throw them out. And if they are valid, then we'll keep them in the mempool, and they'll be eligible to be committed in the next block. So you can imagine a situation, imagine you're trying to double spend, right? So you have 10 atoms, and you send 10 atoms to me and 10 atoms to Joseph, right? And so obviously only one of those transactions can be valid, right? But say Mircea receives one transaction in his mempool that sends 10 atoms to me, and Jarko receives one transaction in his mempool that sends 10 atoms to Joseph, right? And so one of those folks is going to find that eventually that transaction is going to be invalid, right? So what will happen is, say the transaction where you send the 10 atoms to me eventually gets committed, right? And so Mircea will see that block, and he'll say, okay, this transaction's been included in a block. I can delete it from my mempool, right? And Jarko will see that transaction in the block, and he'll say, okay, that transaction's been committed in the block. I have this other transaction that says Igor is sending 10 atoms to Joseph. Let me rerun that over the mempool connection, over the check TX, and see if that transaction is still valid. And the application will see that and say, no, this transaction's not valid. Igor doesn't have any money anymore. He sent it all to Ethan. So if he's trying to send it now to Joseph, that's not going to be valid. And so the application will return in Jarko's mempool and say, this transaction is no longer valid, and he'll remove it from his mempool.
And this depends largely on the ordering in which we are rechecking transactions.
Yeah.
So if you try out like transactions A and B, it might be fine, both are valid. But if you do B and A, maybe like both are invalid. So
exactly.
And like this is happening locally at every node. So and is there some thinking about like this ordering, and like whether we want to try to do something about this, or is there some kind of best practices or like use case where?
Yeah, so there has been a lot of thinking about this ordering. One thing is, it's not, so when I was saying earlier that the mempool is like a reliable broadcast mechanism, I don't think it's exactly reliable broadcast, because it does try to provide an additional guarantee, which is that the order you see transactions in locally is the order you broadcast them to your peers. But because peers can be receiving transactions from anyone, you might have seen a string of transactions that are valid in that order to you. But when they get sent to other peers, they might not be valid because those peers may have seen other transactions that make them invalid. And so it's kind of a best effort atomic broadcast, but it doesn't guarantee that everyone is going to deliver those transactions in the same order at the mempool level, because they can be receiving them in different orders from other peers. Yeah.
And is there some sort of fairness which we implement here at the Tendermint level, so that, for example, transactions which come first will be actually ordered earlier with this mempool ordering logic, or
defined first? I mean, basically, the mempool keeps a single queue, like an ordered list, and transactions are added to that queue in a first come, first served basis. And so if a transaction is valid, it gets added to the queue, and then you receive another transaction, and its validity is expected to be dependent on the last transaction, on the state from the last transaction, right? And that way, if you build up and ordered, a sequence in your own mempool that's valid locally, and then you propose that sequence in consensus, the expectation is that, that will be valid to all consensus nodes.
Cool, very good.
But when we're broadcasting transactions to peers, we send to peers in the same order that we received, right? And so for each peer, we only send it a transaction after we've sent it all previous transactions we've received in the same order. And so it's basically, it's kind of like, think of it sort of like the LMAX disruptor setup, where you have this like concurrent queue that one thing is writing to. So it's like appending to the top of it, right? And then you have a bunch of readers, which are the things sending to peers. And each reader is trying to progress steadily through that queue, one transaction at a time, and sending those transactions in order to its particular peer. And then once it gets to the end of the queue, it waits until another transaction gets added and then sends it, and so on, right? Make sense?
Yeah, so then coming back to the reliable broadcast. So actually it's a reliable broadcast, right? In some sense, you require that the transaction has to stay valid in order that it actually broadcast, right, delivered. If it becomes invalid before, it might not arrive everywhere, for example.
Yeah, so it depends on your definition of delivery. Because I think at the base layer, it actually does implement some version of reliable broadcast for a limited definition of delivery, where delivery just means like you ran checktx. Checktx might return an invalid result, in which case you'll throw the transaction away, but you did kind of do something with it. And so actually, defining delivery in that context gets more subtle, and I'm not sure exactly, what the protocol is we're talking about, but that would also be something that would be quite worth formalizing.
And so in the Archive version of the consensus, there is this valid function or predicate. So do I understand correctly, this is actually implemented at this mempool level rather than at consensus, that the consensus calls valid, or is it happening again?
That's a little different. I believe the validity predicate is really about the well-formedness of the block itself, right? Because the value we're coming to consensus on is a block, and the block has to satisfy certain constraints. It has to be structured correctly, et cetera. It can't just be any arbitrary value. One of those constraints is a dependency on the output from a previous block, which you're expected to already have or to have initialized if you're starting from zero, but it does not depend on executing the current batch of transactions. So the validity of a block in consensus does not depend on executing the transactions in the block.
So it's independent of the application. It's really just more on the, I see.
It's independent of the application for the current transactions, but it is dependent on the application for the previous transactions, because it does depend on the result from the previous transactions. So, for the single instance setting, like single instance consensus setting, it's independent of the application, but from the actual state machine replication setting, it's not. And, so capturing that will probably also be a little subtle.
I guess so, yes.
Does that make sense?
Yeah.
Cool.
Okay, one more question.
Yeah.
We attack from both sides. So transactions are completely application specific, right? You don't have any language, you don't have any, no structure essentially, right?
Yeah.
I see. So it makes it really up to the application developer if they don't mess things up, right?
Yeah.
Okay.
Yeah. So what this actually means, if you look carefully at definitions, is that Tendermint on its own actually doesn't implement atomic broadcast. Because one of the conditions of atomic broadcast is this kind of like only delivery once, only delivered once. Like every transaction can only be delivered once. And Tendermint itself doesn't enforce that. It doesn't guarantee it. It tries on a best effort basis, but the only once delivery depends on the structure of the transaction, right? Because you're expected to have some kind of indicator in the transaction that is unique to it that allows you to enforce that the transaction, that particular transaction is only delivered once, right? So it could be a timestamp, it could be a nonce, something like this, right? And so that condition is actually, we depend on the application to actually enforce that. And so Tendermint on its own, you can't, technically speaking, doesn't implement the standard definition of atomic broadcast because it doesn't implement only once delivery. It relies on the application to provide that. And so Tendermint basically expects that the application will provide that, but it can't enforce it on its own, because to enforce it on its own would mean that it enforces some structure on transactions, and it doesn't do that. Now, insofar as the actual value that we're getting consensus on is a block rather than transactions, then you could say Tendermint enforces only once delivery, because Tendermint only, commits one block for each height. But, then you start to get into the semantics of the definition of total order broadcast in blockchain systems and whether you're delivering blocks or transactions, and, the definitions start to change. But kind of a side point, but relevant probably from a specification perspective.
I have a question here. Only after a block is committed, we can tell if a transaction was valid or invalid.
Yeah.
Is that correct?
Yeah.
And you can only check that from the state update it did or not.
Yeah.
Okay.
Now, no, the transactions can return results. So the application can say, actually, this transaction is not valid. Even though it was included in a block, even though it was committed by all the validators, it's garbage. It's just random junk. It can't even decode it. It's semantically meaningless. That could happen.
Okay.
Yeah. Now this is kind of contentious, because some people are like, I don't want garbage transactions in my blocks, right? Now, we try to guarantee through the interaction between the mempool and the consensus that a correct proposer will only include correct, valid transactions. But of course, a malicious proposer, and there could be up to a third of them, can include complete garbage. And it's up to the application to account for that. So, if so desired, the application can say, well, if you propose a block that has invalid transactions, then you're going to get slashed or something, right? But that's not really enforced at the Tendermint side. The Tendermint side, you can put whatever you want in a block. Some people have requested, and there are open issues about this, a way to actually check the validity of transactions before we vote on them. So that we guarantee that at the very least, say the transactions in a block will pass check TX before we actually vote and commit the block. But that's kind of still an open issue and a discussion whether or not we want to bring that kind of optional early check into the Tendermint.
Right, because in this case, if we slash them for invalid transactions, then there can be issues where, as you said, the ordering of transactions was changed, and that made the transaction invalid. And you don't want to slash a proposer for that.
Correct. And this is why, so again, we do guarantee, or if we don't, it's a bug, that a correct proposer will not propose invalid transactions, regardless, because the expectation is that a correct proposer, first of all, the expectation is the application implemented things correctly, in which case a correct proposer has run all of the transactions they're going to propose in order through CheckTX, and they have all been valid in that order, and therefore they will be valid in the block, even if no one else has seen those transactions in that order yet, right? So that's the guarantee we provide. But it does require some cooperation with the application to make sure that that's true.
But there seems to be here sort of additional assumption. We do ensure that correct proposer will do CheckTX in the right order before building a block. But the executing CheckTX does not necessarily lead to the same result than deliver TX. So you could still have CheckTX passing, but then deliver TX failing.
But so now we have to start to distinguish between different kinds of failure, right? And there are also issues about this, about how we should start to do this distinguishing. So for instance, one kind of failure is the transaction is garbage. It doesn't even deserialize. It's just random junk. That kind of failure should absolutely be dealt with at the CheckTX level. So if you pass CheckTX, you're a well-formed transaction, right? Another kind of failure is signature verification. Again, that should be dealt with at the CheckTX level, so that if you pass CheckTX, the signature is valid. But then there are failures that require more execution, and more kind of stateful information. Maybe you have an Ethereum virtual machine contract and you specify some amount of gas and you run out of gas, right? And at the CheckTX level, we don't execute, for instance, in an Ethermint context, we don't execute the full state machine because it's actually not necessary to provide the guarantees at the mempool level of preventing denial of service. But at the DeliverTX level, of course, we do execute the full state machine transition, like say a smart contract in the Ethereum virtual machine. And we might run out of gas. And running out of gas is a kind of error condition, but it's a valid error condition. It's an error condition that we expect correct proposers to still potentially propose, because all of the other constraints, that the signature is valid, the transaction is well formed, the fees were paid, etc. So the economic guarantees are still upheld. It's an error only for the user, right? The request from the user failed to fully materialize, but from a protocol perspective, the execution is valid, right? So we have to distinguish between failures that are kind of invalid execution from a protocol perspective and invalid execution from the perspective of what the user wanted. And we can't always guarantee that the user is going to get what he wants or what she wants, right? And so those kinds of error results are semantically quite different from malformed transactions or invalid signatures.
Or to simplify this, is there any way that we can check if a transaction failed during consensus, we can go back and check whether it passed during CheckTX. If it did, then we should not slash the proposer.
Exactly. So you need some kind of way to indicate what kind of failure it is, right? And the idea is that if it passed CheckTX and is proposed by a correct proposer, then it's correct for all intents and purposes from a protocol perspective, but it still might fail from a user perspective. And for those kinds of failures, the proposer wouldn't get slashed. But really, at the end of the day, it's up to the application to determine what kind of failures a proposer could or should be slashed for based on what kind of execution they do during CheckTX, right? So if the application does something during CheckTX, then it should guarantee that those checks will be satisfied during DeliverTX. But if there are some checks it doesn't do during CheckTX, then it can't guarantee that those will be satisfied during DeliverTX, and so it shouldn't slash for those. So all of this stuff is really application dependent. But the application knows what kind of error it ran into during DeliverTX, and it knows if it's something it should slash for or not.
So you mentioned CheckTX, DeliverTX. For the newbies out there, are they part of ABCI or?
Yeah, so these are the core messages of ABCI, the workhorses of the consensus and mempool connections, respectively. So I mentioned that a bit earlier. We still haven't actually looked at all the ABCI messages. We'll do that next, but I just wanted to kind of clear up all this understanding about the concurrency and the semantics of these different connections. Any other questions there? Cool. So let's look at the next slide. So this is the definition of the ABCI as an interface in Go. And we can go to the protobuf in a second. It's just easier to see at a high level from here, where we have a set of messages, really a set of methods. So there's a request and a response message for each method. The requests and responses are defined using protobufs, but effectively we have, you know, an RPC system, right? It's a method-based system, and for each connection, certain of the methods may be called, and they're all mutually exclusive. So a particular method is only called on one of the three connections, right? So on the query connection, which is this first one, we have, most importantly, the query method, and we'll look at the request and response for that, but this is really just a read query. Note, it doesn't guarantee fully up-to-date reads, because this query does not travel through the consensus. It's just a query of the local state of the node you're querying. And so if you're querying from a node that's not fully synced with the rest of the network, this query will not return the latest state, right? If you want to enable queries to return the actual latest state of the consensus, you need to write those queries as if they were transactions. That's kind of a side point, but there's also this set option method, which we can ignore because it's actually not used anywhere. And then there's the info method, which is used to initially synchronize Tendermint with the application. So on startup, whenever we start the process, Tendermint calls the info method and provides some information about the latest state, and the app responds with its information about the latest state, and then that's used to basically synchronize Tendermint and the app to make sure that they're at the same state before actually engaging with all the peer protocols. So that, you know, this is basically to deal with cases where they're running in different processes and there's some kind of partial failure or crash failure of one of the processes or the other, and so that one may have lost state that the other has, and we need to synchronize them before moving forward. We could probably do a whole developer session on the details of this handshake, this synchronization. It's subtle and also worthy of being specified. But this is basically critical to making Tendermint a real world production system that allows the thing to crash in various states and be able to recover from crashes basically in any arbitrary state, right? Because there are many ways, you know, you could crash before you've committed a block in consensus, after you've committed a block, but before you've sent it to the application, after you've sent it to the application, but before it's finished committing, after it's finished committing at the application, but before Tendermint has recorded that it's finished committing at the application, right? So there's many different places where the crashes could happen, and we need to be able to recover from any of them. Okay, so that's the query connection. Then there's the mempool connection, which only has the one method, which is checktx, and it basically just passes arbitrary bytes as a transaction and gets a response. And then there is the consensus connection. And in the consensus connection, we break up basically the delivery of a block into a few different messages. So first of all, when the chain is initialized, the very first time when we're at height 0, right? So when we're about to make the first block, the first thing we do is call init chain. And init chain basically takes the Genesis file and passes it through the request init chain and receives responses from the application. And so this is how the application can basically be initialized from the Tendermint Genesis file, and the application can tell Tendermint, if it wants to, what the initial validator set should be. So the initial validator set can be a function of the Genesis file. It doesn't have to be explicitly in the Genesis file, and the application can determine that. And then with each block, we execute the following sequence: begin block, deliver TX for every transaction, end block, and then commit. And we can go through in detail. Begin block basically includes details about the last block that was committed. So for instance, it includes the header. It includes any validators for which there's misbehavior detected. So if the validator has misbehaved, it includes an indication that there's evidence so the application can punish them. It includes a list of all the validators who signed the last block, so we can track liveness properties, stuff like that. Then we call deliver TX for each transaction, and transactions again are just arbitrary bytes. Then we call end block, which is only important for the response, where the response can contain updates to the validator set. So with every block, the application can decide to change the validator set for the next block. And then finally, we call commit, which tells the application, we're done with this block, actually persist it to state, and return to us the new Merkle root of the state. And so with that new Merkle root, the application has persisted the state to this. It's computed a checksum and questions? Cool. So
should we touch on like what another question that's from previous? About...
Yeah, right. So one question here is basically, let me share again, is around, so right now, so one important thing to know about the ABCI is that it's been, the actual implementation is designed so that you can send messages asynchronously, but in order, right? And so, for instance, when we send the check TX, the check TX is, the method is called asynchronously, but the results are expected, they're expected to execute in sequence, and the results are expected to be returned in order, right? So we don't wait, when the mempool calls check TX, we don't wait for the result before we might call check TX for the next transaction, but we do expect the responses to come back in order. And this basically allows us to, rapidly push transactions over the wire, because again, we're expecting that we're communicating with a process, with another process over a socket. And so we have to, serialize these messages and pass them over the socket and deserialize them on the other side. And so we don't want to wait for all of that before passing the next transaction through. And so it's been implemented to be able to do this asynchronously, but to still get everything executed in order and have the results come back in order. And the same is true for deliver TX, right? We don't want to block on the execution of each transaction, but so we just forward them all asynchronously, but expect them to be executed in order and to return in order. Now, a lot of people have requested, so the original design here was basically to ensure that because a block could be quite large, we want the application to be able to start processing transactions right away, even before it's received the whole block, right? And so this is why the block was broken up into these 4 messages rather than, say, be a single message. Because you could imagine an alternative, which would be roughly semantically equivalent and maybe simpler, to just give the whole block to the application, or at least all the information in these methods, and just have a single method that says, here's all the information in the block, execute it, and return the result. The original design decided not to do that because of concerns over the latency of starting the execution, where you had to wait to receive the full block. And a block might be a megabyte, you have to serialize it, send it over the wire, deserialize it, etc. It's possible that that was a highly premature optimization, and that it would have been much simpler if we had just done that. And a number of people have actually requested a deliver block approach to ABCI that actually just forwards the whole block over the connection, rather than doing it kind of one transaction at a time. So that's kind of an open question of whether we want to either change the ABCI for that or to support that as an additional option. And there's still some ongoing discussion around that.
Can a compromise be to have a deliver batch TX, which is a set number of transactions delivered at a time?
Yeah, so that's a nice idea that we would change deliver TX to be maybe deliver TXs, and you would configure when you start Tendermint how many transactions you want to receive at one time. And then Tendermint would try to forward all those together. That's one possibility. Another, though, that I would mention is that a use case recently emerged where, so it's important to note that we actually don't forward the signatures, right? So a block, the definition of a block in Tendermint, it has a header, excuse me, it has transactions, it has the commit for the previous block, which is a set of signatures, and then it has any evidence of validators that have misbehaved, right? And we forward the header in full and we forward the transactions in full, but the signatures and the evidence are compressed to only indicate the identity of the validator. So we don't actually forward the signature information. We don't forward the actual contents of the evidence. We just say this validator signed, and we say, you know, this validator misbehaved. And there have been some requests for the application to actually get access to all of that data in order to build more advanced kinds of applications. And so one possibility is that we have another option for the ABCI, where instead of forwarding the block like this, broken up into messages, we actually forward the entire block with all the components all at once. And so, you know, the trade-off there is that people who want the full block with all the information can get it. People who want the block to come, you know, the transactions to come all at once can get it, but those people will also be receiving all the signatures even if they don't want it. But, you know, from keeping the implementation simple and keeping the optionality limited, that might be a reasonable option. But we're still, I think, kind of exploring how we want to do that. Yeah. Questions?
Kind of with a deliver block, would it lift the mempool implementation up into the application?
No, it wouldn't affect the mempool implementation as far as I know.
But it could allow the application to just handle the mempool themselves and kind of turn the Tendermint mempool off. Or is that something else?
No. So that doesn't quite make sense, because the important thing about the Tendermint mempool is it sends transactions to peers, right?
Yeah.
And so there needs to be some functionality at the Tendermint level that's doing that. There has been a lot of discussion about more application level control over the state of the mempool, for instance, to manage prioritization, right? So the application might want to say that actually this transaction is higher priority than that transaction. And so the mempool should reflect that in the way the transactions are ordered, sent to other peers, and proposed in blocks. And that none of that is currently possible with the current implementation of the mempool. And we may require additional functionality in the ABCI to support that. But as far as I understand, it's orthogonal from the delivered block question.
Okay.
Yeah. Any other questions? I guess the last thing we would do is I'll pull up my terminal and we can go through the actual definitions of these in protobufs, and maybe a few examples of where and how things are done in the code. If there's any other questions first.
I was wondering, like, what is, I know we have some mean of testing ABCI apps without like running Tendermint. If I'm not wrong. Like, can you just comment on this?
Yeah. So we don't have a good story for this yet, actually. We have wanted one for a long time, but no one's really worked on it. There is an ABCI CLI, which is basically a command line interface for sending these protobuf messages over a socket, so that if you implement an ABCI server in another language, there's kind of an easy way to manually test it. And I think there might be a script that runs through sending a bunch of those just so you can like quickly test a server implementation. But we don't really have a good like systematic framework for really testing the functionality of an ABCI server and the expectations of an ABCI server with respect to Tendermint and so on. So that's something that's still kind of an open area of need for us, I would say.
Sorry, maybe I missed something. What's an ABCI server?
Sorry, this should have been clearer. So Tendermint and the application communicate over a socket, right? And that socket is effectively a client-server relationship, where Tendermint is the client and the application is the server, right? And so the application exposes a listener that listens on the socket, and that is really the ABCI server. And Tendermint implements the client, the ABCI client. And Tendermint is responsible for connecting to the ABCI server, for initiating 3 connections, as we discussed, consensus, mempool, and query, and then for sending requests over those connections and receiving responses.
Got it. And then maybe this is an orthogonal question because I have no idea about it, but the light client this is what it refers to, a light client that connects to the ABCI server?
Totally independent, totally orthogonal. Yeah, the light client has nothing to do with the ABCI directly.
All right, cool.
The ABCI server client relationship is purely about the connection between the Tendermint core process and the application process that are running on the same, that constitute the full node. The light client is a different kind of node implementing a different kind of protocol to actually validate data about Tendermint or about the application. But it doesn't really relate to the ABCI server client relationship. The ABCI server client thing is really about, let me just go back to this just so we clear this up. Where is it here? Is really about, well, both of these diagrams help. So in this case, you can think about the Apache web server as a server from the perspective of a user. The user is the client and the Apache is the server. But from the perspective of the web app, Apache is the client and WordPress would run the server, right? It would be a CGI server, say, because they're communicating over a socket, right? And so the same is the case here. From the perspective of a user, the user is the client and Tendermint exposes the server, like the RPC server that we all talk to on port 26657. But from the perspective of the application, Tendermint is the client and the application runs the server. In this case, it's ABCI, an ABCI client and server. So Tendermint is the ABCI client sending ABCI requests, and the application runs the ABCI server serving ABCI responses.
Got it.
Right? Same diagram here. So here we have HTTP client and server, but then here we have ABCI client and server. And so when we say there's an ABCI implementation in some language, what we're saying is there's an implementation of an ABCI server in that language, which is to say a server that listens on a TCP or Unix socket, which you can open connections to, at least 3 connections to, and which handles ABCI requests and returns ABCI responses. And the handlers for those requests constitute effectively the ABCI application.
Got it. Thank you.
Cool. Anything else? Otherwise, I'll pull up some definitions, some code we can walk through. Okay. I think I can screen again. Can you see?
Yeah.
Okay, so I'm in the Tendermint repo. We can go into the ABCI package. This used to be its own repo, but it's been merged into Tendermint. And so you can see here, there's a definition, there's a client implemented in Go. So this is the ABCI client that's used by Tendermint. There's also a server implemented in Go. This server is not used directly by Tendermint. The server would be used by any Go ABCI application. For instance, Gaia, the Cosmos Hub. The Cosmos Hub would import this server, and if it wanted to communicate with Tendermint over a socket, the Tendermint client would talk that, and the server would respond. But if we look at the client, we have multiple implementations. We have a local client, which is really just implementing function calls, right? So in the local client, it's really just direct functions. Really, this application interface, which I showed the screenshot of, it's really just calling direct functions. But in the socket client, we're actually implementing, TCP or Unix communication over some address, right? We maintain a network connection, etc. We also implement, for convenience, a gRPC client. So gRPC is Protobuf's native kind of RPC server. And so rather than our own implementation of an RPC server that supports protobuf, we also support a gRPC version for people that want to get started quickly using gRPC. But gRPC is basically built on top of HTTP and uses synchronous communication. And so it's not as well supported by us, the development team, and it's probably a little bit slower. So we really recommend that people use the actual socket-based implementation or the binary implementation rather than the HTTP one. And then in the server, we have basically the same split. Well, we just have the socket server and the gRPC server. The method calls don't need to be implemented. You don't need to implement the server side for the method calls. That's just the interface. Then if we look at the types, the main thing in here is the protofile. Bunch of imports, don't have to worry too much about. We define our requests. So you've seen all these request types in the screenshot from before, except for the echo and the flush. The echo is really just for debugging, just to actually show that you can send requests, get responses, it's otherwise not used by Tendermint. And the flush is really kind of like an operational concern to actually flush messages across the connection. So when you're actually using the socket, you call flush every once in a while. The client decides how to implement flush, how often it actually wants to flush messages across the socket. That's kind of an implementation detail. If you're just using methods, if you're compiled in process, you don't need to call flush because it doesn't make any sense. There's nothing to flush. So then we actually define all the requests. So info, this was from the query connection for that handshake. This is the information we pass, basically version information from Tendermint. For init chain, we're basically passing in all the key information from the Genesis file, the timestamp, the chain ID, consensus parameters, validators, and most importantly, an arbitrary blob of application-specific bytes. So typically this is JSON, but Tendermint doesn't know how to interpret this JSON. It forwards it to the application, which is expected to understand this JSON. If you look at the Genesis file for the Cosmos Hub, the majority of the Genesis file is a quite large file, is the application-specific JSON that determines the initial allocation of atoms, right? Which is fully application-specific. Tendermint doesn't know anything about it, but there's also some initial state about who the validator should be, which again is application-specific. And then in the response, the application will say, okay, Tendermint, here's what your initial validator set should be based on what was contained in these app state bytes, which only I know how to interpret. Here's the query request. You pass it, we differentiate between data and a path. We roughly expect data to be stored in like a nested hierarchical structure of Merkle trees. And so the path is kind of a path through those trees. There's also different concerns that you might be querying for. And so we kind of isolate those using the path. And then the data is really the actual query you're making for that given path. I mean, you could think of it a lot like a REST call, like an HTTP call where you have some path, which is the part of the URL, and then you have the data, which is like the query parameters, something like that. But this isn't necessarily standardized in the ABCI. It's just really up to the application how it wants to define paths and data. You can specify what height you want to query for, and then you can ask for a proof as well. And the expectation is that the application will be able to produce proofs about the state. So these are basically like membership proofs or non-membership proofs to say that some piece of data is actually contained in the state at some particular height according to a Merkle root for that state, which is contained in a block, right? So these are the links that are basically made possible to facilitate light client proofs so that a client can ultimately make a query that travels through the ABCI that returns a proof that the client can verify using the light client protocol and using the basically cryptographic commitments contained in the light client protocol to actually say, okay, I can verify this proof. The actual specifics of that in the light client protocol and so on are obviously outside the scope of what we're talking about now. So then we get into the block execution. So in begin block, we pass the hash of the block header. So this is the full header. We pass the last commit info. I wonder if I can jump to definitions. Let's see. I cannot. And we pass some evidence. So I'll show you what the last commit info looks like. It basically contains the round that the block was committed and information about each vote. And the information about the votes is quite simple. It contains the validator and whether or not they signed the last block. So it's just a Boolean that says they signed the last block or they didn't. And the validator is basically just an address and a voting power, right? So all we're passing along is the address and the voting power, and then whether or not they signed the last block. And so note, we don't actually provide the signature over the ABCI, so the application doesn't actually check if the validator signed the last block, because Tendermint did all that already, and it's just informing the application, this validator signed the last block or this validator did not. And the application can determine how it wants to use that to incentivize uptime, basically. And so for instance, in the Cosmos Hub, it uses this information to say that if you're a validator and you've missed some fraction of the last X blocks, then you get some punishment, right? And that in that way we can kind of incentivize the validator set to stay online, say, and to be signing actively to get, even though we only require 2/3 of the validators by voting power to actually commit a block, we incentivize 100% of them to do so using this kind of mechanism. And then, so that's the last commit info. And then we also have evidence, which is again, just a reduced form of evidence. It doesn't contain the actual proof. It doesn't contain the actual evidence. It's just indicating to the application, Tendermint detected some evidence of misbehavior. This is the validator it corresponds to. This is the height it corresponds to. This is the type of misbehavior, the timestamp, and the total voting power at the time of misbehavior. And again, there are some issues around how we're doing this, and there are some requirements or some additional information that the app might like. And so the evidence actually is a bit of a work in progress, as we've discussed in previous dev sessions. Okay, then I'll quickly say a couple other things, then we have to wrap up. The request check TX. So when we do check TX, we're basically passing a set of arbitrary bytes, and then we're passing a type. The type, this is actually a recent feature that only got added like this summer, I think. There are 2 types currently. There's new and recheck. New indicates to the application, this is the first time we're seeing this transaction. Recheck indicates to the application that actually we've already sent you this transaction, but now we're sending it again because we recently committed a block and this transaction was not included in the block. And so we need you to recheck it to ensure that it's still valid given the latest state of the block. But it's possible that some of those checks don't need to be redone because no matter what happened in the block, it's not going to change. So for instance, signature checks, right? So validating a signature is not really a stateful operation. It's purely functional based on the public key and the signature. And so if you've already checked the signature, this allows you to signal to the application that you don't need to check it again, right? And so that allows performance improvements at the application layer. Request deliver TX just has the arbitrary bytes. There's no types there. End block, the request doesn't actually have any useful information. It's all in the response, and same for the request. So those are the requests. We can look quickly at the responses. There's a response for every request. There's also this exception response, which is a theoretical thing that's not actually used yet, but this is in theory a way for the application to indicate I've experienced some kind of exception. We need to fail. Really what is expected to do now is just panic, and the operator is expected to intervene at that point. That's a whole other discussion, how to deal with errors over the ABCI. Echo flush, we don't care about. Info is for the handshake. We should probably have another session on how this information is actually used to synchronize Tendermint in the app. Set option, we don't worry about. Response init chain allows the app to set the initial parameters and the initial validator set, as we've discussed. Response query, contains responses to the query. It includes some kind of response code, non-deterministic logging information, just to be nice to the user about what happened, key and value from the query, proof, and so on. This code space stuff we can talk about some other time. One thing that's worth, I guess we're running out of time, and there's a few other things that were probably really valuable to talk about, like events. So events are the way that results can kind of be sent back over the ABCI, and that things can be indexed, right? And so an application on any ABCI message like begin block or deliver TX or end block, events can be emitted, which are basically, an event is basically a list of key value pairs, right? You can say, this is some event that happened, and here are all the attributes associated with that event. And then transactions and blocks can be indexed according to those attributes, so that at some later time, a client or a user can make a query that says, give me all transactions where the following event occurred, right? And the event could be something like, you know, where this account was a sender, right? And Tendermint doesn't know anything about accounts or any of these application level things, but by including information in events, Tendermint can then index things according to events, allowing users to later query for them. So this is how we build out a quite advanced query system for users to be able to say, you know, give me all transactions that affected my account, or that affected your account, or that affected this validator, or whatever, right? And so there's actually quite a lot of detail in there about how that's done. And there's this whole transaction indexing machinery within Tendermint, and this is all exposed over WebSockets so that clients can subscribe to events and so on. Ultimately, we probably want this stuff to be offloaded into some kind of more mature SQL database. And there's some initial work on this and future work on this as well. Check TX and deliver TX return a bunch of information. Again, there is a response code. They can return some data, some non-deterministic logging information, information about resource usage. Again, we could talk more details about that. Also events. End block, this is where the validator updates come in. So the application actually must track validators if it wants to be able to update them, so that it can tell Tendermint, you know, here are the updates we're making to the validator set. And there are restrictions and expectations on how the application is dealing with this. And again, that's something that should be better specified. And then finally, the commit contains what is expected to be the hash of the state, which is included in the next block. So that's a high level summary. We're basically out of time, so I don't want to keep going. If there are any final burning questions for the last 2 minutes, we can field those now, or we can come back to all this at some future date. I hope this was helpful and provided a lot of context for people on how ABCI works. And we'll see you next time. Any final questions?
I am good. This was amazing, actually.
Yeah, this was great.
It cleared up a lot of things that I didn't even know I was confused about.
Awesome.
For me as well, this was super helpful, I feel. Thank you so much.
Yeah, you got it. Thanks everyone for your attendance and your great questions. We'll see you next time.
It will be a lot of fun formalizing and specifying.
Oh, yes.
Yeah.
Looking forward.
Yeah, me too.
Just to finalize, Bucky, you think we should do a 2-part series on this? So it's like either we do it next week, or we just kind of hold next week, we do a different subject.
Yeah, we can do it next week or some other time. There's probably a bunch more things that are worth going through, like some of this code space stuff, more details on the event system, the handshake, which interacts with the info, the request info, response info, and some of the implementation details of how this whole server socket thing, client server thing is done, and some of the expectations Tendermint makes. We can go through the documentation and talk about the expectations. I would just point out, actually, the last thing I'll show you is on the website where this information is. So I'm going to share again my screen here. So here we have tendermint.com/docs. So there are 2 key, besides the protobuf file, there's this ABCI spec. So there's a little bit of an overview here. And then the key things for application developers are the methods and types and the applications. So there's also this client and server thing that explains how the client and server are implemented. But then the methods go in detail about the 3 connections that we talked about, how errors are handled, a little bit about the event system, determinism, all this kind of stuff. And then for each message, details about the request, the response, and then the usage. But this is all really the syntax of the ABCI. The semantics are contained in this application developer guide, where we talk in detail about the connection state, the interplay between the different connections like we were discussing here, rules around transaction results and validity, validator set updates, crash recovery, all the kind of semantic information about how the connections are managed and so on. So if you're looking for more information, you can read through that. If you think anything can be further clarified, pull requests are of course welcome. This is all contained in the Tendermint repo. Cool. Thanks everyone.
All right, see you next time.
Thank you.
Take care.
Thanks.
Thanks.
Thank
Bye.
you.